There's no symmetry breaking going on, but you can still have a quantum critical point because you, in that circumstance, you'd have a line of first order transitions ending in an endpoint, and this is going quantum critical because you're tuning the endpoint towards t equals 0. Okay? And we're also able to study various thermodynamic crossovers that show that the thermodynamic scales are being suppressed on exactly the same range of temperature and fields as the transport looks anomalous. And you can also then study the electronic part of the specific heat as you go across the phase diagram, and you see that the electronic part of the specific heat has a very strong rise, and it's actually a 1 upon reduced field divergence is going on until the divergence is cut off in the middle by some strange stuff, and the strange stuff is actually associated with the formation of some new phases, right? So in the language of this bandwidth and crystal potential, the interesting thing is that quantum criticality is also a way of changing the bandwidth. So you're using the magnetic field to tune the quantum critical system, you're reducing the characteristic kinetic energy scale without to first order changing the lattice potential. So that's probably why you're able to frustrate all of the interaction, the kinetic energy and the lattice potential. It's by playing this quantum critical game.
Sorry,
yeah.
The Fermi surface on both sides?
The Fermi surface is, it's measured on both sides. It's different because just in the same way that a ferromagnet at its TC will polarize its Fermi surface into a different spin up and spin down one, that's what happens in metamagnets as well. You have a field-induced Fermi surface polarization, and that can be seen. But it's all metal everywhere. We can even see quantum oscillations in the anomalous phase. So there's no question that these are all metal-metal transitions. So I know from bitter experience that you don't see anisotropy unless you explicitly look for it, because in the early years when we had this phase, we knew that what happened to the resistivity when we had the field along the c-axis was very surprising. There's an offset slope here, but there's at least a factor, approximately a factor of 2 jump in the resistivity when you enter some anomalous region, and the resistivity jumps back down again on the other side. Now here, if you measure, with hindsight, when you measured rho A and rho B, or rho X and rho Y, you get more or less the same thing. Right? That's because the field is in the high symmetry direction, and here there's been nothing, we believe, to break the symmetry that gives you domains of hard transport in X and hard transport in Y. So what we then thought is this system probably has some spin-orbit coupling. So if we rotate the sample in the field, or equivalently add a small in-plane component to the field, maybe we can couple to this. It's a magnetic system after all. Maybe we could couple to these domains if they exist and induce an anisotropy. Right? So in other words, this is microscopically anisotropic, but we can't observe it because we have macroscopic domains. Can we play with the domains? That was our logic. And gratifyingly, we were able to. We thought we might see a tiny effect, but we saw a huge effect. So essentially, along the easy direction for the transport, you completely kill the extra scattering that was giving you the big rise in resistivity, whereas along the perpendicular direction, it looks exactly the same as before. So gratifyingly large response. And what then really caught our notice was that we could do the same in our tilted field as Eisenstein was doing because of the symmetry breaking of his device. And the development of the resistive anisotropy looked uncannily similar in both cases. And actually, even in the 2-degs, you can play with in-plane fields as well. So you can add an in-plane field component to the out-of-plane field one, and you can tune the anisotropy almost identically, phenomenologically at least, to the way we were able to tune it in this oxide. So we were, at that point, very excited and pretty much convinced that the microscopic physics of these two systems had to in some way be the same. So, and this again, I'm just saying again, here you're quenching the bandwidth by going into low Landau levels. Here we're always working in a metal. We're at Landau level 200 or something. We're at very high Landau level. So the Landau quantization isn't killing the bandwidth, but I think the quantum critical tuning is, and that's how you're able to get into the same region of parameter space. So after a lot of work that's summarized in a paper from last year, after a lot of work, we realized that this material had a slightly complicated phase diagram where thermodynamically we can absolutely convince ourselves that these are first order transitions with the red vertical and black vertical lines. We can absolutely convince ourselves, and I'll show you in a moment, that this is a second order thermal phase transition, and we believe this is a second order phase transition as well. We can use vector magnets, similar to the ones that I saw in Herman's lab earlier this morning, to establish that the transport is within very high precision, exactly fourfold out here and out here, but it's strongly twofold in the presence of tilted fields in both of these regions. So the order parameter looks slightly different from transport point of view, but the basic fundamental point is that you've gone from fourfold transport to twofold. If you've got keen eyes and you are used to systems like this, you'd see that this was rather strange, because if we're saying this is a first order transition, it's bowing out the way as a function of field instead of being some form of a dome, which would be the more usually seen shape. And that has thermodynamic consequences, because that predicts that the entropy as you cross this boundary actually goes up. So you're going from a low entropy state to a higher entropy state by entering a phase. And although that can happen in standard pneumatic liquid crystals and it can happen in liquid helium, it's not impossible, but it's unusual. So we went away and checked this quantitatively with some careful thermodynamic measurements. I won't bore you with the details of it, but we were able to confirm that yes, indeed, the entropy does rise, and it rises reasonably substantially as you cross that phase boundary to go into our phase. So that's a pretty unusual situation within correlated electrons, that you have phase formation accompanied by this rather significant increase of entropy. Things also look very strange as you come down into the phase from above. So first of all here, I'm showing you what happens as you just study the electronic specific heat as a function of temperature coming down outside the phase, and this is stylized, meaning these are fields substantially below and substantially above the phase. And in both of those cases, you see a boring C upon T, which just flattens out at low temperatures, showing that you've made a crossover into a standard Fermi liquid state. As you come down into the phase with the black arrows, wherever you come down into the phase, first of all, you see a small kink in the specific heat as you cross the roof, which is consistent with it being a second order thermodynamic transition. But then when you're in the phase, the specific heat C upon T continues to go up slightly as the temperature goes down. And that again is very unusual. You don't expect to see that. And it certainly doesn't look like the signs that you've gapped away things as you've gone into the phase. And you can rationalize it with a bit more knowledge. If I quickly go back to the phase diagram here, in many quantum critical systems, for reasons which again aren't fully understood, if you study the specific heat, the electronic specific heat, not as a function of field but as a function of temperature, you see a weak logarithmic divergence of that specific heat as you come down. And we also see a weak logarithmic divergence of the specific heat as we come down in temperature here. But then something else happens, of course, when we hit the TC of the phase. So what we then realized was that if we replot the same data as this, but on a semi-log scale, if we replot it on a semi-log scale, there's the logarithmic divergence in the normal state above the superconducting transition temperature. But what you then realize is that when you calculate the entropy balance based on extrapolating that weak linear dependence in the phase and extrapolating the logarithmic dependence outside, you get an entropy balance perfectly at TC. So probably that's telling you that you do have a second order phase transition, but it's a second order phase transition coming out of a very unusual state that it's not common to see at all, and we still don't fully understand why we're seeing that. Whatever else, and I'm saying this, you'll see in just 1 second why I'm stressing this point. Those thermodynamics do not look like the thermodynamics of a gapping transition. Because if you had a gapping transition, you'd be, typically, There's no board. I wouldn't be popular if I drew on this. But remember a BCS superconductor, right? C upon T would come down like this line to the normal state, and you get a beautiful jump of your specific heat, but then it drops right down to 0 because you've gapped away, so you have no states. We not only have plenty of states left here, we have more states left than you would expect in a standard metal. So I was at this point absolutely convinced that this was some unusual form of pneumatic transition associated with quantum criticality. No way it could involve translational symmetry breaking or a gap. Absolutely not. Nothing looked like that. Then my good friend Steve Hayden at Bristol posted on the archive a couple of months ago a beautiful paper where they've discovered that they do indeed see translational symmetry breaking in the spin system, and they see it not only in our what they now call our A phase, they see it in our B phase as well. They see it with a slightly different Q vector in each of the phases. And a lot of the phenomenology that they're seeing associated with it agrees with some of our transport phenomenology. If you've got good eyes, will see that he's insisting that this is a standard spin density wave in the way he interprets. My point is, it's incredibly interesting what he's done, but you can't ignore all the thermodynamics. The thermodynamics still look extremely strange. So this is not a standard spin density wave. This is a state with some form of spin texturing. In our language, it's asmectic, but we do not yet fully understand what the significance of this translational symmetry breaking is. My message is, while I like the experiment very much, I think it's a huge oversimplification just to say that this is an SDW, because you can't explain many of the other observations that way. But it's certainly very interesting for the future of work on this compound.
You also find a negative slope there.
Yes.
Okay.
A negative slope with what? Sorry. No, okay. This is neutrons. So these are plots based on other people's data, including ours, the black lines. The white dots are where they did the neutrons. And even getting to do the neutrons at 5 fields required a lot of persuasion. But after arguing with him for a while that I wasn't sure that I believed the neutron results, they've also now studied the temperature dependence at each of these fields. So it's not really dots, it's lines that they have. I completely accept the validity of his result, and that he's seeing the onset of texturing of the spins at the same TC as we see the onset of the thermodynamic signature. I agree with all that. I just don't think that you can be as simplistic as saying that you now understand everything that's going on. So that's the status report for strontium-3 ruthenium-207. Now I'd like to spend the last few minutes going back to the cuprates with the hook that just because you see a smectic state in a system like this doesn't mean the interest's over. Actually, far from it. So I know you have a big STM effort here. Here's some STM data that were basically taken years ago in Seamus Davis's group and published about 2007. These numbers mean that they're 2 different cuprates. And they can find energies when they study the conductance maps that they see these rather strange local ladder-like viewpoints, or ladder-like images of conductance. And this is detail which is on the subatomic scale. So there's a copper atom, there's an oxygen atom position and a copper position. So this is contrast to do with the actual copper-oxygen bonding. So A, it's amazing technologically that you can see this kind of thing. B, it's now very gratifying that having had this work ignored by many people, now people are beginning to understand exactly what it means and exactly what the significance is. And the significance is the following. This is now taken directly from the web from one of Subir Sachdev's talks, but back in 2010, Metlitsky and Sachdev looked again at what you could call a density wave physics, or in our language, it's smectic physics. And they pointed out that you could write down the form factor of a density wave in the same hierarchy that you would use for the form factors for the internal wave function of superconductivity. So again, it's coming back to this analogy between the particle-particle channel and the particle-hole channel. And what they showed is that it's simple to do it. You can, a standard CDW would have what's called the S-wave form factor. You can have an S-prime type form factor, like the form factor of the superconducting gap in many pnictides, or you could have a D form factor, and there's a further series that you can just go on in. It's a decoupling you can do. They then realized that what was seen back in 2007 is actually the conductance pattern corresponding to a D form factor density wave. And Seamus Davis and I work with some shared PhD students, so one of these shared students has been heavily involved in the analysis project to really confirm that this spatial pattern, if you transform it into K-space, really agrees with the D-wave form factor. So it seems that the smectic that you're seeing in the high TC superconductors is a smectic with a D form factor. That is not nearly as easy for me to understand intuitively as the D form factor in a superconductor in a nearly antiferromagnetic metal. But there's a beautiful paper on the archive at the moment which gives a lot of the history to this, again from Subir and a collaborator, who point out that this is really helping them to narrow down the types of Hamiltonian that you might want to do to study this system. Because a very simple Hamiltonian based on antiferromagnetic physics has a D-wave superconductor as its leading instability in the particle-particle channel, but it also simultaneously has a D form factor density wave as the leading instability in the particle-hole channel. So it doesn't get the orientation of the D density wave correct. So there's some excuses being made in here for how you might adapt that to a more exotic theory. But I think what I really wanted to bring out is the general principle that you know, we have the Hubbard model. We know some of the solutions of the Hubbard model. It's very significant in our field. But everybody's trying to come up with some model Hamiltonian that seems to get the key physics of the cuprates and the pnictides correct. And one of the ways they're going to check that is to be looking at these electronic liquid crystal states and trying to see what sort of form factors they have in reality and in relation to these model Hamiltonians. So I think it is, and this is a very nice discussion of it in this paper, which